Last time we studied connections on a principal bundle, and we saw that a connection, which was just a distribution of horizontal subspaces, which was a choice, there is no canonical such distribution, that this could be expressed quite conveniently as a Lie algebra valued one form on the principal bundle. And today we will study how this Lie algebra valued one form on the principal bundle can be expressed locally as a Lie algebra valued one form on the base manifold. And that is how you usually meet it in physics, and depending on context, it's then called the local connection coefficients, gamma, in, say, general relativity, you may have met that, or the Young-Mills field if you do elementary particle physics. So today's chapter is 5.5, local representation of a connection and we will use invariantly the terminology Young-Mills fields. And we'll put that in quotation marks because that may apply to situations that a physicist would not call a Young-Mills field in the first place. So what was the situation? So let's recall that in the last lecture we considered a principal G bundle. So we had a principal bundle P with total bundle space P, a right action by some Lie group G, a projection down to some base space. And on there we considered a connection in terms of a Lie algebra valued one form omega. So the one form aspect of it is that it takes you from a section of the tangent bundle linearly to, and that's now the Lie algebra valued aspect of it, to the Lie algebra of the underlying group. And it had to satisfy two conditions. First, whenever you plug in the vector field on P, xa, that is generated by a Lie algebra element A, the one form sends you back to this A. And B, if you consider the pullback under the right action of an element G on the group G, then on this form, once you plug in an X, this equals add G inverse, push forward. I'm sorry, these brackets are wrong. So you pull back the form and then you apply to an X. And this is the add G inverse, push forward of omega. You first apply the X, so the result is a Lie algebra element. And on that, of course, the push forward of the adjoint map at G inverse can act. So this was a connection one form. Now somebody asked the question, what precisely is this mathematically a Lie algebra valued one form? Well, the simple answer is exactly this. It's a map from the section of the tangent bundle into, not into C infinity of P, not into the real numbers or some number field, but into this Lie algebra. And I can, of course, call this a Lie algebra valued one form, and you may ask, to what extent is this still a one form? It's a nice name for it, it's maybe a suggestive name for it, but in what sense can I still treat this as a one form? In what sense can I not treat this anymore as a one form? And one particular question one could ask, so this is some further explanation on how this is to be read. One particular question is, assume we have a map U that takes us again to this P. And you know, if we make this commute here, so we have the U here again, you know, if this is this U together with the F is a bundle morphism, a principal bundle morphism, then it's already a principal bundle isomorphism, and because this is the same P, this is already a principal bundle automorphism, principal bundle automorphism, which is just an isomorphism that goes back to itself, therefore auto. Okay? If you have such a principal bundle automorphism, you know that there are these two compatibility conditions that the diagram commutes here and commutes here. We wrote this down several times. But now the question is, if on here lives a Lie algebra valued one form omega, well, let's say on here lives an omega of this type, if it's a one form, we should be able to pull it back via this U. So we should be able to consider U pullback of this omega. Okay. But now the point is we defined the pullback of a one form if the result was in C infinity P, right? Or in the number field, if you work at a point. We didn't define this pullback if it's Lie algebra valued. So a worry could be, do all the things we define for one forms and we are heavily using, like pullbacks, do they generalize to this case? And in fact, even more so, they don't only generalize, the pullback isn't affected at all by what the destination is. I'll show this here. So you know, the pullback, you apply this to a vector on here, okay? And you know that the pullback is defined as the omega of the push forward of this vector. Because of this object here, the pullback of omega, is as much Lie algebra valued as this guy is, because the pullback defined in terms of the push forward, this is just a normal vector. The pullback doesn't care about where you land. That's the thing, okay? So it's a very valuable question to ask whether I'm just abusing terminology. I slickly call this a Lie algebra valued one form, but did I even check that everything works? Well, everything works this way. If you're in doubt, just go back to the definition of the objects and you'll see it works. Okay? So hence this is a very clever way to look at it, to say it's a Lie algebra valued one form, because the one form aspect isn't harmed by changing the destination there. Okay, but if in doubt, you should always check. This is one example. Okay, so now what we're interested in is we have this bundle and we have this one form globally defined. That's not a problem, and that's the connection. However, in practice, we often want to restrict to some part of the bundle over some subset of this base manifold. So in practice, for instance, for calculational purposes, one wishes to restrict attention to some subset U of the base manifold, such that the situation is P down only to some U. So we look at this restriction of P. I don't need to write this down. It's clear what I mean. Okay. And we wish to study the bundle only over such a subset of the base manifold. Now, if you think, for instance, of this base manifold in physics as space-time or the physical space you're interested in, and this is just the principal bundle of the transformations that you consider, okay, this is not only for calculation purposes and so on, but physics always takes place locally, right? If we want to write down physical laws, we do local experiments, and then we write down the laws. So naturally, we'll be in a local patch, and it's then kind of a matter of extrapolation in physics that we extend this globally. So physics actually very often starts in a local patch, and the globalization is another issue. Now, one thing we would like to do here, and I'll show you in a second a natural definition for something like this, we would like to choose a section that goes from a section of this principal bundle, which we call sigma, on this local patch. So choose a local section, sigma u to p, and you remember that the section is such that pi after sigma is the identity on u. That's the definition of a section. So we choose such a local section here. And what can we use this for? Well, this local section induces two things. It induces, first of all, a so-called Young-Mills field. Again, I put it in quotation marks. Young-Mills field, which we call omega u, where the u refers to this region here, which is now Lie algebra valued, or it's still Lie algebra valued, but it's now only a section, it's now only a one form on this local patch on the base manifold. And so the key thing is this is part of the base manifold, whereas here this was the principal bundle. So this guy omega u lives somewhere else, namely it's defined as the pullback of the omega that lives here. So this is where the connection one form lives, omega, and here is, of course, where the pullback lives, which we may call, or which we call omega u. That's clear. So this Young-Mills field, omega u, lives on an entirely different level in this picture. That's important to realize, okay? So this is called a Young-Mills field. Now, this section does another thing. This section can also be used to define a local trivialization of the principal bundle. So what is a local trivialization? We call it H. A local trivialization is a map that takes this local region, attaches to each point of it the group, and maps this into the bundle. So you see, if the entire bundle, now apart from the principal bundle business, if the entire bundle is of the form base manifold M cross G, then it's a trivial bundle, okay? Now, the principal bundle is only trivial if it admits a global section, or it only admits, if and only if it admits a global section. So hence, in general, we can't have a global section. That is why we had to restrict to a local one here in the first place. But then a local section will give you a local trivialization, namely such a map. How? Well, you take an element little m in U, an element G in the group, and you map this to sigma of M acted upon from the right by G. Because, so a point M in here is first lifted by the sigma to a point in here, and then the G moves you in the fiber. Okay? So again, the section does two things. It allows you to pull back the connection form to a Young-Mills field, and it allows you to understand part of this P as this local trivialization. And once you have this local trivialization, then you can define the local representation of the connection 1 form as the pullback of omega under this H. Okay? So what kind of guy is this? Where does it live? Well, we have to extend this picture. So we have a map from U cross G into P. That's this local trivialization, right? This map was induced from here. And of course, here we still have this projection map. There's now the projection to the first factor, no doubt. Down here we can put the identity. Of course, we can act on here from the right by some primed action with G. We go U cross G, then we have the H back. Okay, so we have this full diagram. Now this will not be an a bundle isomorphism, because this is only part of it, but we can pull back the omega along here. So pulling back the omega along here, you get the Young-Mills field. Pulling back the omega here, you get the H star of omega, and that lives on this local trivialization. Okay? Now, if we had to guess which of these two, the Young-Mills field or the local trivialization, contains all the information in the omega, we would probably guess this local trivialization, I mean locally, should contain all the information in the omega, and that's true. But now, pulling this down to the base manifold, we might feel there is some information missing, but that's not the case. Also, in this local Young-Mills field that lives on here, all the information that's contained in this guy is also contained in that guy. And of course, these two contain less information than this, but only because they are only defined over a local patch of the base manifold. But over this local patch, this guy and this guy contain the same information as this one. And now we write down the relation between this local trivialization of the form and the Young-Mills field down here. And in physics, we usually only write down, I mean, in local coordinates, we write down this Young-Mills field. So the A mu potential in electrodynamics is such a Young-Mills field. The A mu Lie algebra valued field in non-abelian gauge theories is also the Young-Mills field down here. The connection coefficients in differential geometry, say in general relativity, the gamma, mu, sigma, whatever, they're the Young-Mills fields down here. So they're all these Young-Mills fields. They can then immediately, you can construct this guy from them. I write down the formula in a second. And these are all kind of the local shadows, the local representatives of the abstract, everywhere defined connection 1 form. And these connections are important because they come up all the time. Questions so far? Okay. I should emphasize here, so here the H star of omega, if H goes from here to here, then the H star of omega, of course, goes from, so at the point M comma G, goes, of course, from the tangent space of mg at the point mg of u cross g. It goes to the tangent space of the h of that of the p. I'm sorry, it's the pull, no, it's the pull back. This, I wrote down some push forward, I'm sorry. So we start somewhere in the cotangent space here, or the sections of that, okay, at the point. And the point I wish to make is that from here we go to the cotangent space of at the point mg of u cross g, and now that's my central point here, and this is isomorphic to the cotangent space. Doing the right thing here? No, it's a form. It goes from the tangent space. I'm sorry. So again, so this is pullback is a form, but as a form, it then takes was right what I wrote. It takes a vector here. So it takes an element of mg u cross g, and my central point is this is the tangent space at M of U direct sum with the tangent space of G at G. And from there, it takes you here. Okay? So this is the central point here. And the theorem is that the connection between this guy and the Young-Mills field is that H star of omega, so we pull back here, applied to. So I need to apply this to an element in here, but that's a pair of a tangent vector to the base manifold and a Lie algebra element. So let's call the tangent vector V and the Lie algebra element gamma. So this is an element of T U at the point x, so this m, this is at the point mg. And this guy here is an element of t, g, g. It's not at the identity, it's at the general point g of the group. I wanted to make give an example first. Anyway, this is fine. And this equals, well, I promise there will be a relation between this local trivialization here and the Young-Mills field. And the Young-Mills field omega u appears here, and of course it can eat this tangent vector v. Thus it will produce a Lie algebra element, which will then be pushed forward by add g inverse push forward. That is this. But that's not all. There is actually an extra term which needs explanation. And this extra term comes by this capital Psi at the point G acting on the gamma. And I need to tell you what this object is, where this capital Psi G is a map that takes you from TGG, so from the tangent space to the group at the point G. Well, it better does because it eats this guy. It takes you to the tangent space at the identity, so that is where we usually think of what we usually think of as the Lie algebra. By virtue of the following map, you can take any tangent vector at a point and you can understand it as the value of a left invariant vector field on the group generated by a Lie group element. We did this several times, right? So you may need to go back for the definition of this guy, but I just mentioned it, and it spits out the A that generates this. Okay, so let me make a picture. So assume here the surface of the sphere is the Lie group. We have here the identity, so there's the tangent space to the identity. Let's assume here we have the Lie group element G. There's a tangent space here. So we are at the tangent space here, and we take an arbitrary vector from this tangent space, say this one. Then there is, we found that there is always a specific vector A up here, such that the left invariant vector field generated by this A this guy reproduces this vector here. Okay? And this map is kind of the inverse. You take the vector here and you find from which vector it has been produced. This is what this map does, and this map is called the Maurer-Cartan or Cartan form. Because it is a form, because it's a form on the Lie group, because it eats a vector and it yields, so it's the Lie algebra valued 1 form, so it's a Lie algebra valued 1 form, but now on the group. Before we had Lie algebra valued 1 forms on the principal bundle total space, that was the connection. We had a Lie algebra valued 1 form on the base space or part of the base space, that's the Young-Mills field. And now with the Maurer-Cartan form, we have a Lie algebra valued 1 form on the group. But you already see from my explanation or from what we did before, this is fixed. This is a property of the group, what its Maurer-Cartan form is. And I'll give an example in a second of how, for example, the Maurer-Cartan form for, say, the general linear group looks like and how one calculates it. Okay, good. So let's, questions so far? So let me provide some examples. So again, you should notice that all this construction is only needed because we have this wish to represent the whole thing on the base space, right? Yeah?
There's a question concerning the small L you just noted. Where is that actually meant to symbolize?
Where is that what?
The small L, what is that actually?
The small L sub G was this left multiplication on the group that sends an element G twiddle of the group to G twiddle. And then the L sub G push forward, therefore it takes you from the tangent space to the tangent space. So from TGG to TEG. For instance, from TEG to TGG. That's the push forward, and that's pushing forward this A along the left multiplication on the group. I think we defined this, calling, yeah, of course, long time ago. Okay, good. Okay, so example 1, and this is supposed to be an example for the motivation to choose particular sections. So you might have wondered, okay, we want a localization, but why do I have to provide as much information for that as to choose a section? Well, consider the frame bundle as an example. Remember the frame bundle, so that is where the total space is given by this LM, and where you attach to every point all possible bases to the tangent vector. That's the frame bundle. We discussed this, I think, at some length. And now any choice of chart, of a coordinate chart, ux, on the base manifold M, induces a section, induces a particular section on the frame bundle, namely given by sigma of, at a point M, where this M is from the local chart domain, and you simply choose the frame that is provided by this choice of coordinates. So d by dx1 at the point M up to d by dx dim M at the point M, right? This is a frame. So you go to a point in the base manifold that's covered by some chart domain. You have your coordinate map. And now to this point, you attach the frame that's induced from the coordinates at that point. Very natural. Okay? So choosing coordinates down here on the U in the frame bundle immediately induces a section, namely this one. So it has to do with the choice of coordinates. And then the Young-Mills field omega u, which is defined as the pullback of omega under sigma, hang on a second. Yes, so that's a one form. It's a one form on U, and it's Lie algebra valued. So that's Lie algebra valued. But what's the Lie algebra here? Well, the group is GL dim M, comma R. And what's the Lie algebra of GL? Well, it's any dim M times dim M matrix, right? And so with components, we can call the components of this guy omega u. It is a one form on U, so it has a space-time index, well, space-time, a base manifold index down. You can also put this one back here. And then it has a Lie algebra index, but this GL, these are linear maps, invertible linear maps on R dim M. So there is an index up I and there's an index down J. Well, this is not a GL matrix, but it's the Lie algebra representation. Okay? And these guys you usually call gamma I, J, mu. And you see the mu runs from 1 to dim M because it's a one form on this part of the manifold M. So mu runs from 1 to dim M. But the I and the J, they also run from 1 to dim M. Why? Well, because this is GL dim M. And so very often we write gamma, alpha, beta, gamma. We pretend that all three indices have something to do with the base manifold. But they do not really. These two here are the indices labeling the elements of the Lie algebra, the matrix elements of the Lie algebra, whereas this mu is a proper one-form index. These are the connection coefficients from general relativity. Well, if you choose an orthogonal frame and so on, so it's an extra restriction. But so these are the ones from differential geometry, from more naive differential geometry. These are the gammas. So these guys have different logical status, these indices, even if they run over the same range. Okay? So that's an example, and it's an example how these Young-Mills fields come up by choice of a section, and for the frame bundle, this is immediately induced by a choice of coordinates, for instance. Okay? So you don't only choose the region. So that was the first example. Now, the second example, are there questions? Okay. So the next example will be an example for the calculation of the Maurer-Cartan form also for the example of the Lie algebra being the general linear group. Why is the general linear group so important? Well, because the Lie algebras we're looking at, or the Lie groups we're looking at, very often are either the general linear group or some subgroups thereof, right? So that works then essentially all the same. So GL is a good case to discuss. And now I said here we have this relation between the local trivialization of the connection 1 form on the principal bundle in terms of the Young-Mills field down here, plus this extra bit, but this is fixed by the Lie group. So we should be able to calculate this guy for any Lie group at hand, and I'll demonstrate this for the GL group. Okay? Construction of the Maurer-Cartan form. For the Lie group G given by GL D, R. So this has really only to do with the Lie group at hand. And so the first thing we do, we choose coordinates containing on G, on the Lie group, containing the identity. Containing IG. So that's part of G, well, say some connected component here of the identity. And we can consider, of course, the general linear group as a matrix represented by matrices. So we choose coordinates xij, a double label, and we go down here to RD times D. Well, D by D real matrices these are. There is one determinant condition. The determinant doesn't vanish, but that's an open condition. Okay, so and we take the ijth coordinate of an element is just the ijth entry of the corresponding matrix. That's a coordinatization of this Lie group. So xij of a group element G, we will take as the matrix entries there. That's it. So in a sense, this is the definition of the matrix entries as always. Okay, that's this. So now consider a left invariant vector field, namely the left invariant vector field L that is generated by a Lie group, Lie algebra element A. So this A is from the Lie algebra here. And we look at this guy at the point G. We know that exists because it's a Lie group, yeah? Yeah, that was just supposed to be that part of G. Choose coordinates on an open set GL plus of GL containing the identity. So it's a chart domain where, okay, yeah. Pardon me? That is right. So the X lands in RDD. Thank you very much. The X lands in RDD, but then we take Xij's that map to R, because every single coordinate is a real number. Thank you. Yes. So now let's consider such a left invariant vector field, and we on this group, and we know that it exists, okay, and it can be actually applied to such a vector field to any function. So in particular, it can be applied to the coordinate functions, because that's the business of vector fields. They act on functions, and I can let it act, and I evaluate at the point G, which still lies in the chart domain. Okay, so we know this guy exists abstractly. Now we want to calculate this guy. So what is this? The action of a vector field on a function? Well, by the very definition, you take the function and you let it act on what? You let it act on the curve to which the vector field is tangent. Now the point is that this tangent vector field is tangent to G dot, that's the dot in the Lie group, exp of TA. And then you take the derivative with respect to this t, so this is the with respect to t derivative, and you evaluate at point 0. Now is this right? You take a point G of the Lie group, and then you multiply with the exponential map of t times A. This t times A, this is the one parameter subgroup generated by the A. If t is 0, this is just the identity, so you're at the point t, and if the t increases, you move away from the point G. So this is a curve. This is a curve gamma of t, right? Where for each t, the guy lies in G, and gamma of 0 is the little g. This is a curve in the Lie group through the point G. Aha. And its derivative, after you applied this function, is of course just the application of the left invariant vector field acting on here. Okay, so it uses here the idea of the left invariant vector field, how it is generated, because the exponential map is just defined as the integral curve of this left invariant vector field. So you go back and forth there, that's this definition. And at the same time, we applied here the definition of what actually the action of a vector on a function is by its very definition. Okay, so there are several definitions going into here. Right, so we'll need this, because you know that for the Maurer-Cartan form, we want to associate with the LA the A, so we need to understand the LA. Good, so now how does it go on in this case? Now, we have here, by this coordinatization, we have a matrix group, right? A group of matrices, and the composition on GL as linear maps is of course mapped into the by this coordinate transformation, mapped into matrix multiplication of the representing matrices. Okay. Now the same is true for the Lie algebra elements. We already used this before. They're also labeled by these indices because they're just the tangents to these curves in this matrix algebra. And what I actually want to say here is that this x here is just e to the ta if I actually take the coordinatization. Well, it can be calculated by really exponentiating these matrices. We did this in one of the problem classes. I talked at some length about this. So this can be done. Then you derive at position 0. Okay? And now before we execute this derivative, however, we convert into matrix representation using this guy acting on here and pushing one in between. Anyway, at the end of the day, it's GIK ETA KJ, all of this derived with respect to t at point 0. But of course, this is a fixed matrix, so it only acts on here. It pulls the A in front. It evaluates at 0. The result is GIK A KJ times the identity. Quick check. We have a vector field on the group. We have functions on the group, which are in this case coordinate functions because I like to put these ones in. The result should be a real number dependent on ij. Oh yeah, two matrices multiplied, and I take the ijth entry of the matrix product, because this is nothing but the matrix product. That's of course a real number dependent on ij. Yeah? These? No, they should. It's the without taking?
Without the chart map.
No. I said no. No, look, this is, if I said something like this, I didn't mean it. So the point is xf, the definition of a vector, where the vector is understood, and that's what we do here, understood as the vector according tangent to a curve in a point P, that is f of hang on. F after gamma yeah, exactly. This is f after gamma, and that you can derive. And that's it. So this is f, this is f, and this is the curve gamma to which this is the tangent vector. Hence, the derivative at 0, if gamma of 0 is indeed this point P. This I check, gamma of 0 is indeed this point G. Should be fine. The brackets must be outside. That works. Okay, good. It's just a definition of how the vector acts. Okay. So this is this, and then of course we do not want to have this applied here like this. We can just conclude from this that it has the components. These are just the components of this vector field. So LA G is therefore simply G I K A K J d by dx ij at the point G. So all the indices are gone. This is a basis of the tangent space to the Lie group at the point G. Of course, the vector field at this point is an element of the tangent space at this point, and these are the coefficients. This is summed over, and these two guys here are also summed over here. So this is the left invariant vector field for the Lie group element A of the Lie group to GL at the point little g as an element of GL. That's the left invariant vector field. Now, the Maurer-Cartan form can now be read off. What was it again? It was this capital Xi at the point G takes a tangent element to the group at G back to the Lie group element, so the tangent element at the identity, such that LAG, I can always represent an element here as this, is mapped to this A here. And so if I want to achieve this in general, I have to define, well, not in general, but for this example, so here, I have to define this as G inverse of IK, G inverse of IK dx. Right, so because there's a form on here, so it must have kj indices. So this is now the co-basis. Of course, it's a form. And the result lies in the Lie algebra, but we coordinatize, so it has indices ij. This is at the point G. I write an at here for clarity. It's not an index. So this is the Maurer-Cartan form. So let's check why this is true. Why do I write down this now after I found this? Well, I can now take the Maurer-Cartan form and I plug in the LA up there. Take it at G, plug in the LA. So what is this? This is G inverse of IK, so IJ, IK dx kj and I feed into this one form, I feed this vector. I feed into this in this vector, but now I need to choose different dummy indices. So P R A R Q d by dx PQ. I feed this into there. Now this yields G inverse IK. These guys are constants. They pull out GPR ARQ. And then I have the dxkj acting on the d by dxpq. Well, but they're of course dual by construction. So that yields a delta k P and a delta qj. So if this is right, then the k becomes a p, so it's G inverse IPGP R AR, and the q becomes a j. But here the matrix multiplication produces another delta IR, so this is AIJ. Oh, fantastic. You plug in the left invariant vector field generated from A, you get back the AIJ if you already have this coordinatization here. Done. Okay? So the lesson is, if you want to calculate the Maurer-Cartan form, calculate how the left invariant vector field acts on the coordinate functions on the group, on some chosen coordinate functions. You want a local representation of the Maurer-Cartan form. You find this, and then you read off, you have to kill this guy in front, because the L is actually the A. Well, in this GL case here, it's like this. The L is the A, but there's the G multiplying it, because you're at the point G. You've got to get rid of the G in front in order to get the A. Well, that's just what happens, okay? So this is the calculation of the Maurer-Cartan form for the GL group. Okay, so what we saw is that if we have a connection 1 form on some principal bundle, and we now look at some part of the base manifold. So here we have the connection 1 form. Then by choosing a particular section sigma, we can pull back this connection 1 form to this Young-Mills field sigma pullback omega on the base manifold, and this will be a Lie algebra valued 1 form on this domain. And as I mentioned before, so this is the Young-Mills field, and this is the connection 1 form. As I mentioned before, in physics, we very often are prompted to write down a Young-Mills field because we understand the situation locally, and we can then speculate about whether we can construct a global connection 1 form out of various local pieces. And as you know, that if you have a manifold here, then you may look at various local pieces. You can look at the local piece U1 or the local piece U2, and you may look at U1, U2 domains that intersect. And then you're in business because you understand the situation here, you understand a Young-Mills field here, and on another patch U2, you understand the Young-Mills field. Now, certainly there will be some compatibility condition required concerning to what happens in this overlap, okay? And exactly this compatibility condition we're now going to study. So, well, let's take this picture here, where we go from P down by pi to here and by pi to there, and let's assume we really have non-intersecting domains on the base manifold. And then correspondingly, we can choose sections sigma 1, or in this case sigma 2, and here a section sigma 1. And if we have a connection 1 form living up here, we can now have two different Young-Mills fields on U1 and in U2. Here obviously sigma 1 pullback of omega, and here lives sigma 2 pullback of omega. And what we will be particularly interested in is what happens, what's the transition between this one and this one if I restrict attention to the domain where they're both defined. Okay. So if I want to know this, I introduce a gauge map, and that's an object we call traditionally omega, and this omega is defined on the intersection of U1 and U2, so it's a function on the intersection of the domains on here. And it yields an element for each point, an element in the gauge group, okay? And it's defined as follows, such that, also defined as the unique omega of M for all M in U1 intersected U2, for which we have that the sigma 2 at the point M in this intersection is obtained from the sigma 1 at the point in this intersection by right action of the group element omega M. So I have two different sections on this intersection, and I generate one from the other by acting on one with this omega M. And this is always possible, and it's always uniquely defined because of the free action of G on the principal bundle. So this kind of intertwines between the two choices. We're only interested in that. And then the theorem says, then, so under the above assumptions, the Young-Mills field omega U2, so the one on U2 defined with respect to sigma 2, this Young-Mills field is given as the adjoint now of omega inverse at point P, of omega inverse at point P, acting, P is bad, M, because this is a one form on the base manifold, or rather only on this intersection, which is part of the base manifold. Push forward of the U1 plus the pullback of the Cartan form at this point, at M. Is this right? Yes, that's right. Okay? So if you wish, you can make explicit the character of this as a one form at the point M. So you say it's at the point M, it's a one form. So this is a one form, and this is a one form. Okay? And then you see how this whole business acts. Okay? So it looks similar to the other formula. It's an entirely different formula. It says how one connection, think of the connection coefficients, how it's expressed in the other frames. Okay, that's the theorem here. Now, before we come to a proof of this, let's work it out again for the GL case. because that's usually the best way to understand this, because this is rather formalistic. So what do we need to do? We need to calculate what is actually this add omega inverse push forward on this in the GL case, and what is the pullback of the Cartan-Maurer form with respect to the omega in the GL case. And let's start with the latter bit. So we calculate the, so example, for G equals GL dr, and the frame bundle, we calculate omega pullback of the Maurer-Cartan form. Of course, the result will again have these indices because the Maurer-Cartan form is Lie algebra valued. So we have this, and we do this at the point P. And we remember that the omega itself goes from U1 intersected U2 into the group, and the Maurer-Cartan form takes you from TGG to TEG in the fashion described before. Okay, so how do we do this? We need to apply this to a so it's a form, the Maurer-Cartan form is a one form on the group, which means we can act on a vector d by dx pq, because that's a tangent vector, and if we now this guy can act on there, we pulled it back, so this will be such a vector at the point P on which we will act. If we can calculate this, we can calculate the entire object. No, nonsense. Sorry. Okay, so it's true the Cartan form would act on that, but now we pull it back with the omega, so that means that the pullback of the Cartan form, of course, acts on the tangent space of this intersection, right? And is then Lie algebra value. That's what I wrote down first today. If you have the pullback here, so we act on an x mu at a point P, but now the point P is 1 in U1 intersected U2. That's what we do. So this guy we want to, so this is just to get straight what we want to do. We understand this guy if we understand its action on every tangent vector. Okay. So the pullback, of course, is the push forward, is the form here at omega of P now, ij, applied to the push forward of this guy under this guy. So this is the omega of P push forward, acting on del x mu at the point P, and the whole result is then of course at the point omega of P, as it must be such that this form can act on it. So that's the definition of the push forward. Okay. So what's the next step? Well, we in the GL group, we already know what the Maurer-Cartan form is in GL. Maurer-Cartan ij down G is G inverse. So in this case, omega inverse at the point P, or omega at P inverse, I k, and then because it's a form, these are just the components, it's dx kj. Okay? And this guy still acts on this gentleman over here. Nothing changes, so it's the push forward d by dx mu at the point P, but the whole thing is at the point omega of P. And so is this guy. Okay? So far, so good. So, how does it go on? Yeah. So now here you have a covector, so you have a dx kj acting on a vector. What's the definition of this d? Well, it's that this vector actually acts on this function, right? So this is omega of p inverse I kth component. Now this vector is omega push forward d by dx mu p is, however, now a vector at omega of p and is a tangent vector to the group, because the omega lands in the group, so the push forward is a tangent vector in the group, acting on the functions xj, kj. Right? It's the action of the function. It's the definition of the d. But now we use the definition of the push forward. This is omega of p inverse I kth component. Now the definition of the push forward of a vector is that you apply the vector d by dx mu p. You apply it to what? You apply it to the function that's this one after this one, xkj after omega. Okay? Aha, but what is that? Well, the omega, omega of p, all of this of p, right? Because we're at the point p now, acting here. Now, xkj of omega, omega of some point p is a group element. So this xkj are just the kj coordinate of that group element. So we can write this as omega of p ik. Then the derivative d by dx mu at point p of the kjth component of the omega. Inverse, yeah, that was what I'm, exactly, inverse, kj. Okay. So, but that means if I calculated how this pullback acts on such a vector, if I want to free the expression of this vector, so if I want to write down just the pullback of the Cartan form at the point P, components I, j, then it's of course all that's written there, it's omega of P inverse I k d by dx mu omega of P k j times dx mu, because this index here in this component goes there. Well, it's clear, because if I then act on this vector again, this is delta'd and has gone. And so what you often do here is that you say, well, so this is the spatial derivative on the base manifold of this group-valued gauge function omega times the dx mu. So what you usually do, but this is really a definition of what you mean there, you write this as omega of p, omega of p, or even without the p's, it's clear, it's all at the point p, omega inverse, and now we say it's a matrix because it is, so we make it fat. It's not the components of the matrix, it's the matrix. And this guy here we write as d of the same omega. Because they're matrices, between them there is a matrix multiplication, and this guy you just write as the d of this omega. Okay? That's it. So the pullback in the GL group, the pullback of the Cartan, Maurer-Cartan form with respect to the gauge function is this omega inverse d omega. You must have seen this before with gauge transformations in physics, I guess. Okay? And so there is no more, apparently, it looks like there is no more side of the Maurer-Cartan form, but it's of course in this very special structure here. But the omega is just the gauge map that interpolates between the two different sections one has chosen there. Okay, so that's the first part. Is there a question so far? Yeah? So all indices are gone up to the I and the J index. And this is a matrix. You take the inverse. This is a matrix product. And the resulting matrix has, of course, indices. So that was the first part of this gauge transformation formula, or rather the second summand. And the first summand requires us to understand the, well, it's still continuation of this example. Now try to understand, or now calculate the add omega inverse of p push forward of omega u1 part in the case of P equals the frame bundle and therefore G equals the GL group. Now, this is not too difficult because we recall that the add of some G is the map from G to G such that an H in G is mapped to GH G inverse. So this is an action on the group. And now we wish to figure out explicitly what the push forward is. You see the add map had this this interesting property that if you start here on TEG, you're of course being sent to T and now add of EG, but add E, well, add GE, but add GE is of course GE, G inverse is again E, so this is again the Lie algebra you're mapping to. That's the appeal for the action on the Lie algebra, that it sends you back to the Lie algebra. And now the question is, how does it act in practice? And in practice, the remarkable thing is, claim that add G star, the push forward, acting on a Lie algebra element A, so this is from TEG, that this is actually given by G A G inverse, and again I make this fat because this is the matrices representing the respective elements. And that sounds like I forgot that I put a star here because it sounds terribly similar to this one, but the point is here, this is the group multiplication in or on G, whereas here it's matrix multiplication, and I use the fact that both the group and its algebra can be represented by matrices. But it seems surprising that this happens like this, but it's not so surprising because you remember that a tangent vector is the derivative to a curve in the group. And the push forward of a tangent vector is actually the derivative to the push forward of the curve, which is just the curve mapped by this map here. But this pushing forward is not a curve. It doesn't depend. If you then take the derivative, it's not affected. The only thing that's affected is the thing in here, and the two guys out there, they remain there. It's very easy to check this. Okay? So the edgy star is here like this. So in some books, they even forget the star at this point. They just write edgy on A, which is terribly misleading because the edgy acts on the group, not on the algebra. It is still the edgy push forward, but it just naively, if you think of matrices, it acts as if you could just plug in another matrix here that is an algebra element rather than a group element. But formally, it's really the push forward. So careful, because especially in many physics books, they start confusing this at this point, only because of this kind of numerical coincidence. Okay, so if we take all of this together, then we get, so all together, we find that on the principal bundle, which is a GL dim M R principal bundle, the change of the transition between two Young-Mills fields, so the transition rule between two Young-Mills fields on the same domain, so on this intersection, on the same domain U1 intersected U2 is, so omega U2, so the second one, is a one form on the base manifold and has these Lie algebra indices ij of the Lie algebra of the general linear group. And it's given by this omega ik acting on the first Young-Mills field with its tangent space index and its index KL of the algebra. And then again comes the omega. Aha, and here's now the inverse here because it's with respect to omega inverse, and here I calculate the add with respect to G, so the inverse is there. L, J, that's the part we just wrote down. I could have written this with fat omegas and fat capital omegas and fat small omega. That would be this version. And then there is the piece from the pullback of the Maurer-Cartan form. And there we saw that's also an omega inverse, ik. And then here we have the d in the sense to be understood as defined before, d omega KL. And in fact, if I write here the mu, then this just becomes the del mu. Yep, that's right. Okay, so this is how one Young-Mills field needs to transform to the other if they're on the same domain. Now, of course, in practice, you will rather have a Young-Mills field defined here and here and here, and if they are to stem from the same connection one from up there, you need to require this as a transition function. And this is kind of the coordinate approach to connections, that you say you have lots of connection coefficients, but going from one to the other, they must transform as this does. And then there is one global connection on the principal bundle that corresponds to that. And so let me write down a final insight from this, which should yield a formula you know. In this formula here, it's entirely kept open which section sigma 1 and sigma 2 you chose. This is true for any such chosen section. Remember, this is just a pullback of the global omega under sigma 2, and this is the pullback of the global omega under the sigma 1. I haven't said what sigma 1 and sigma 2 are supposed to be, but in this generality, the formula is important. But the formula you know for for transformation of connection coefficients is, of course, the one where these sections have been induced by coordinate choice. So application, just one application. Now return to the special case that sigma 1 and sigma 2 are sections from U1 to P to LM to the frame bundle and U2 to the frame bundle, induced by choices of coordinates. By choices of coordinates, namely on U1, you have a choice of coordinates, let's call them x, down to RD, and on U2, you have a choice of coordinates y, down to RD. And then you have the corresponding frames induced. Okay. And then this omega that you have here, then the omega ij is just a Jacobian. Oh, and now we need to check whether it's the right way around here. Xi, yj, let's try this way around. This is this guy. Then, of course, the omega inverse ij is that guy, I dxj. Okay, it's this way around. And what you then also do, you see here, we still kept this mu on both sides the same, but what you usually want to do, you want to express this second one in terms also of the new coordinates that you chose on the second patch, ij. And if you do that, okay, you need yet another Jacobian here. So you need dx, well in this case it's dy mu by dx mu prime. And this is in front of the remaining formula because you also wanted to transform this guy. And then what you get here is dyi by dxj I hope this is right. So then comes the form here. So the only thing that could be wrong that x and y in this formula are exchanged. We have to check in a second. Here you have the ik. You have ik. You have the kl mu. This mu goes with this one, fine. And then comes another dx l by dy j. So let me look at this already. So the L and the mu must go the same. Yeah, and of course I got it wrong. So here it's the y, and there it's the x, and here's the x, and there's the y. I'm sorry. So this is the x, and this is the y. And therefore, is this the y, and this is the x, because the L and the mu, that's right. So that's this part, but then comes plus this part over there. That's the omega inverse. This is d by dxi by dyj. And now here comes another del mu. So there is now a second derivative. There's anyway the omega is the y by dxj d y k by, sorry, this is also an k down here, yk by dxl, but then there's another d mu, so it's another dx mu here, and then the bracket closes. And I think you recognize this as precisely the, so there's a 2 here. You recognize this as the transformation formula for the gamma symbols. Okay? And as I said, this extra bit seems to be absent here. So the gamma symbol, the standard rule is the gamma symbol is transformed in each of these indices like a tensor plus an extra bit, but there seems to be one transformation matrix missing here because there are 3 of those. Well, that is because you also transform this one, which in this formula is kept unmodified, because this formula doesn't suppose that the omegas have anything to do with the transformation of the coordinates. But once you do this, once you go to this special case, this is all linked and you obtain this formula. So what do we now see? So we see that the transformation of the gamma symbols in standard differential geometry, right, of a connection coefficients as you have them if you come from some covariant derivative or whatnot, that these transform in this funny arcane way because we have to look at this stuff locally. But throning over this object with this very funny transformation behavior where it's always emphasized that the gammas do not transform as a 1-2 tensor only because they have indices 1 up, 2 down. That's true, but nevertheless, this complicated transforming object, this Young-Mills field, comes from a very simple geometric object, namely from a global 1 form, which is tensorial, but it's not a 1 form on the base manifold like the Young-Mills field. It's a 1 form on the principal bundle. Okay? So this shows that on the principal bundle, a connection is something very simple. A Lie algebra valued 1 form with these 2 properties. Whereas if you push it down to the base manifold by force, it acquires this very complicated transformation behavior. It looks like something very new, very complicated, and so on. But that is just because you force it down to the base manifold, which may be the point where you start with physics, because you look at it in a patch and you patch it together, obeying this transformation rule. But then it's the inside that you go up to the principal bundle, and everything becomes very simple in terms of the connection 1 form we discussed last time, and which itself is just a convenient encoding of a choice of horizontal subspaces, which is the actual idea of connections. So in principle, everything we did today, we only did because we had to pay tribute to what we usually write down in physics. Okay? And of course, for certain calculations, it may be useful, it must be done. But next time when we discuss parallel transport on the principal bundle and associated bundles and then come to the covariant derivatives on vector bundles, we will not need this anymore, right? We can use it, but we won't need it. So today was just tribute to what is usually done in Young-Mills fields and connection coefficients and so on, but we will go back to the realm of the nicely defined Lie algebra valued 1 form on the principal bundle.